Well, a random variable takes numerical values that describes the outcome of some chance process. And so the probability distribution of a random variable gives its possible values and then their respective probabilities. So we are going to look at two different types of distributions. The first, a discrete random. A discrete random variable has countable number of possible values. Okay, just for fun, do a quick little survey. How many of you speak more than one language fluently? Raise your hand. More than two? More than three? Okay, there was a survey. We said, imagine selecting the US high school student at random. Define the random variable X as the number of languages spoken by the randomly selected student. The table below gives the probability distribution of X based on a sample of students from the US Census at School database. Okay, this is an example of a discrete random variable with its respective probability distribution. And so part A says, show that the probability distribution for X is legitimate. Okay, how do we know it's legit? Okay, all the probabilities are between 0 and 1. And the sum of all of them should be 1 or close to 1 in this case, as it may be. So we say all probabilities are between 1 and 0. And sum of all probabilities equals 1. So part B says make a histogram of the probability distribution and describe what you see. Ah, yes, remember that. Histograms. Have we forgotten? That's okay. We have a little semester exam coming up in the not too distant future, which will incentivize us to remind ourselves of everything that we have, I'm not going to say learned, but been exposed to previously. So let's make a little histogram. So I'm going to put the number of languages here on the x-axis. 2, 3, 4, 5. I'm going to label it. This is number of languages. On the y-axis, I'm going to put the respective probabilities. Point 1, point 2, point 3, 7. And then I'm going to use the probability distribution to fill those out. So this was 0.63. Then almost 0.3. And then like that. And then these are very small. Something like that. What's the shape of my distribution? Skewed. It is right skewed, which makes sense, right? In the context of the problem. It is much less common for a randomly selected student to speak 4, 5, 6 languages than 1. Yes. It's like the joke. You ready for a joke? What do you call someone who speaks 3 languages? Trilingual. Somebody that speaks 2 languages, bilingual. Somebody that only speaks 1 language. Kind of funny. But I digress. We're not here for jokes, we're here for stats. Okay, so I'm gonna say the probability distribution is right skewed. Why is it right skewed again? What are we looking at to see if it's right or left skewed? We look at the tail. Okay, and so part C says, what is the probability that a randomly selected student speaks at least 3 languages? Okay, so symbolically, we write it as probability that X, where X is defined as the number of languages spoken. We want to know the probability that X is greater than or equal to 3. And so that's going to be probability that X equals 3 plus the probability that X equals 4 plus the probability that X equals 5. And so we are going to add up those respective probabilities. So let's see, that was 0.065 plus 0.008 plus 0.002. So that gives me 0.075. And so let me write a little summary statement. There is about a 7.5% chance a randomly selected student speaks 3 or more languages. Speaks 3+ languages. And that leads us to this. The blank is the mean of a random variable X with many repetitions or observations. And this is called the expected value. And this is a fairly important concept that has a lot of different applications. All right. Let me just go through this quickly. I'm not going to spend a whole lot of time here on the mean and the variance because our calculator will do that, but let me show you the math behind it. Okay, here's the formula. Suppose that X is a discrete random variable with the probability distribution here. The mean is this. We're going to take the outcome, multiply it by its respective probability, and do the same thing for the next outcome and add those 2 things together. So you take each outcome, multiply it by its respective probability, and then add them all up. Okay, so it says calculate the expected number of languages spoken by a US high school student. Okay, so we want e to the x. So we're going to take the first outcome, which is one language, multiply that by its probability, which is 0.63, plus the next outcome, which is 2, times its probability, which was 0.295 plus 3 times 0.065 plus 4 times 0.008 plus 5 times 0.002. So take your calculators, if you will. You don't have one, grab a calculator. And let's calculate the expected value. So we're gonna multiply each outcome by its probability, add all those up. So I got 1.457. Okay, so notice, especially if this is a discrete random variable, this answer doesn't really even make sense in the context of the problem, right? Because it's not really possible to speak half a language. I mean, I was gonna throw in another dad joke there, but one per class, right? So I'm just gonna move on. However, expected value is a fairly important statistical concept that has a lot of different applications, okay? So you just need to know that if it's discrete, okay, these are countable. And so the expected value is 1.457, but it doesn't really make sense in the context of the problem. But that's okay. The other thing is that this is always in a long series of repetitions. Okay, so turn the page. And that leads us to this, which is the variance. So the variance is an average of the squared deviation of the values of the variable x from its mean. Okay, let's do a little review, right? Variance is standard deviation squared. And what's the standard deviation? In your own terms, it's
Or.
thinking correlation.
Oh.
Mhm. It's how far something is on average from the mean. Okay, so, and like I said, we're not going to worry too much about this because your calculator will calculate this for you. But let me show you the math. Okay, so we have a probability distribution. You take the outcome, x, subtract the mean, square that. That eliminates any negatives. And then we multiply that by its respective probability. And then you do that for each of the outcomes. So going back to the previous problem that we did, okay, the variance for the number of languages spoken, it would be 1 minus the mean, which is 1.457. And then we square that. And then we multiply that by its respective probability, which was 0.63. And then we're going to add the next one. So it would be 2 minus the mean, which was 1.457. We square that, and then we multiply it by its respective probability, which was 0.295, and so on. We would do that for each of the outcomes. Okay, and so for the sake of time, I'm going to give you the result. It's 0.45. So that's the variance. To get the standard deviation, we're going to take the square root of that. And so the square root 0.45 would give me 0.671. So it also asked me to interpret that standard deviation. So I would say on average, the number of languages spoken varies about 0.671 from the mean. That leads us to this. That's a discrete. The next thing we're gonna look at is continuous random variable. But before we do that, let's have a little fun. And let me say, I'm serious about this. This is legit. Okay, so here we go. I got $20. I want you to choose a number between 1 and 25. It's written down here on my notes. If you get it right, I will give you $20. You paying attention now? August, what's your number?
17.
Mabel?
16, 17, 18.
24. 3. 19.
2?
8. No.
25. 12. 10.
13.
Well, I am happy to say nobody got it. Let's play again. Let's go. Let's make it interesting. Let's go 1 to 15. I said pick a number between 1 and 15. 1 through 15. There's 23 of you in here. 1 through 15. Yes? We'll start over here. Go, Hannah. Pick a number. Right?
15. 4. 1.23.
4. 1.3. 12.
Hi.
You're
Square root. Mhm.
1.9.
Should have done the square root of 2 or something.
4.2.
Well, I'm sorry. Nobody got it. I'm gonna keep my money. Well, and just so that I'm not accused of being unfair. Riley, what was the number? 7.186432961. Nobody got it. Well, here's what I should have done, right? I should have charged you a quarter to play, because then I would be, let's see, what, $21 richer right now? That's what the lottery does, right? But here's my point in doing that little exercise. I did say choose a number between 1 and 25. I did not say a whole number or an integer, right? And so I like the pi, right? Well, a continuous random variable takes all the values in an interval of numbers. So the probability distribution of X is described by a density curve. Remember that? I'm going to assume you don't. We looked at that in chapter 2 with the normal distributions. What is the area under any density curve? It has to be 1. Which aligns up with the sum of all the probabilities in a sample space, right? Now we're tying this together. The sum of all the events in a sample space also has to be 1, but what's different about this is that it's a continuous random variable. Therefore, it can take on any value in the domain. So the probability of any event is the area under the density curve and above the values of x that make up the event. Okay, so I want you to hold on here. Let me see if I can hurt your brain a little bit. That's not a bad. I will not apologize for making you think. So we have a density curve. What is the area of the curve? Has to be 1. This says, what is the probability that x is between 0.3 and 0.7? So I'm going from right here to right here. So to find that probability, I would find the area under the curve from 0.3 to 0.7. So that's a rectangle. It has an area. The width is 0.4. The height is 1. Therefore, this probability would be 0.4. Okay. Well, what's the probability that x is less than or equal to 0.5? Say that 0.5 is right there. Again, I'm going to find the area. It's a rectangle. The width is 0.5. The height is 1. So this would also be 0.5. All right. Well, think about this. What is the probability that x equals 0.8? And the answer to that, Mabel is correct. The answer to that is 0. So think about it like this. I'm thinking of a random number between 1 and 25. What is the probability that you select that number if that number, I'm not talking about integers, I'm talking about any number between 1 and 25, or let's do 0 and 25. Owen, you want to guess a number? You want to lay some money down and try and guess that number?
Infinite.
There's an infinite number of possibilities that it could be. Okay, well, think about this. The probability that it's exactly 0.8 is the area of the line at 0.8. What is the area of a line? It's 0. So think about this. This is where I'm trying to hurt your brain a little bit. How many lines are there from 0 to 1? There's an infinite number of lines. And individually, they all have an area of 0. However, collectively, if I were to take all of them together, what's the area? The area is 1. So I'm adding up 0 plus 0 plus 0 plus 0 to get 1. It's like calculus BC students. It's like what? It's like it's like an infinite series, right? You can have a finite sum, right? So the probability of each line from there to there individually is equal to 0. However, I add them all up and I get 1. Just like you trying to guess a number from 0 to 25, if it can be any number in its domain, it's like the odds of you winning the lottery, right? Not going to happen. I'm still waiting for one of my former students to come back. Wave their winning lotto ticket in my face of my new house. I'm rich now. I'm still waiting. All right, maybe it'll be you. Go play. I'm kidding. Don't play. All right. Well, let's do this. What is the probability that X is less than or equal to 0.5 or greater than 0.8? Well, those are mutually exclusive, right? I would add the probabilities together, so that's gonna be 0.5 plus 0.2. So this one would be 0.7. What is the probability that X is greater than 0.8? That's gonna be 0.2. What about this? What is the probability that X is greater than or equal to 0.8? These two things are what? They're exactly the same. Because the probability that it's exactly 0.8 is 0. So where are we going with this? Well, normal distributions, remember those? Yes. Normal distributions are probability distributions of a continuous random variable. We saw this in chapter 2. Recall, we've got in with parentheses where we have mu and sigma. It is shorthand for a normal distribution with mean, mu, and standard deviation sigma. If X has a normal distribution of mu and sigma, then the standardized variable, remember that, it's called a z-score. We got X minus mu over the standard deviation, and the standard normal variable has the distribution with a mean of 0 and a standard deviation of 1. So we're gonna look at like 2 more examples, okay? Things get slightly more complicated tomorrow, so I'm gonna leave that for tomorrow. All right? But let's look at 2 examples here. It says the weights of a 3-year-old female closely follows a normal distribution with a mean mu of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. What is the probability that a randomly selected 3-year-old female weighs at least 30 pounds? Okay, so on the AP exam, sometimes they get a little picky about notation, so make sure that you follow me here. This is a normal distribution. And I know that because they tell me. So if it's a normal distribution, I've got N. What's my mean? Mean is 30.7. Label it. That is mu. Standard deviation is 3.6. Label that. So I need a sigma. And I want to find the probability that X is greater than or equal to 30. Because it says, what's the probability that they weigh at least 30 pounds? So if I were to make a quick sketch, got a normal distribution. This is 30.7, which is the mean. Got standard deviations over here, 1 sigma, 2 sigma, -1 sigma. Now I want to know the probability that it's slightly less than 30, which would be that shaded region. So if it's a free response question, you need to find the z-score. So let's do that. I've got z equals X, which is 30, minus the mean, which is 30.7 divided by 3.6. And so somebody help me out. What's my z-score?
-1.94.
Okay, negative.
First,
It's
negative
point.
0.19.
There we go. Has to be negative, right? It's below the mean. And if I want to find the probability, you have stats friends. You like hang out on the weekends, or you just like say hello to them as you walk by them in the hall. I want you to like hang out with your stats friends, right? How would we find the probability? It's your stats friend. of a class party, right? So I can reintroduce you to your, wait for somebody to say normal CDF, Newhouse, normal CDF, right? Dying up here, normal CDF, that will give us the probability after we find the Z-score. What's my lower bounds? Whew, semester exam is gonna be great, right? The lower bound is negative 0.19. The Z-score, the upper bound is positive infinity. Mu and sigma are 0 and 1. And why are these my bounds? Because I'm trying to find the probability that x is greater than or equal to 30. And this is the Z-score associated with 30 in the context of this problem. So take your calculator, since it's been a while, find normal CDF, put in the bounds, and let's get a probability. What do we got? Somebody help me out. 0.575. 0.58. So let me write a little conclusion. There is about a 57.5% chance a randomly selected female is at least 30 pounds. And I ran out of room there. So that leads us to this. Last example here. Ah, yes, back to the pick 3 lottery. We've kind of looked at this before, but let's look at it again. You win $500 if your 3 numbers are chosen. So I'm going to choose a random digit 3 times. And then there are 2 possible outcomes. So my probability distribution has 2 outcomes. I either win $0 or I win 500. So what is the probability that I pick one random digit at random? It would be just one digit. It would be what? 1 out of 10, right? There's 10 digits, 0 through 9. Probability that I pick one of those would be 1 out of 10. What's the probability that I pick the second digit at random? It's also 1 out of 10. And these 2 events are independent. Therefore, I'm going to multiply them together. And the probability that I pick the third random digit would be 1 out of 10. So the probability that I pick 3 random digits would be 1/10 times 1/10 times 1/10, or 1 out of 1,000, or 0.001. Well, that's the probability that I win. What's the probability that I lose? It would be the complement of that, right? So this would be 999 out of 1,000. Okay. So the next question asks, and let me preface this by saying, this is a very basic, simple example. But casinos and gambling commissions and all of this, they have calculated all of this stuff ahead of time, of course. What's the expected value? That would be the mean of the probability distribution. So I'm going to take the outcome, 0, multiply by its probability, which is just zero, of course, plus the next outcome would be 500 times its probability, 0.001. And 500 times 0.001, don't even need my calculator, is what? It's 0.5. So the expected outcome is 50 cents. However, right, you don't get to play the pick 3 for free. They're gonna charge you. Probably gonna charge you $4 or $5, right? But just for the sake of simplicity, let's say you paid $1 for the ticket. So in the long run, you end up losing 50 cents. Well, notice, it's not reasonable to say you will lose 50 cents on one play because we are talking about after playing multiple times in the long run over time. For example, if you play 1,000 times, how many times are you expected to win? Once. So you just made $500, right? No,
Oh, sorry, you lost 500.
because what did it take? What'd you pay to play? You just paid $1,000 to win 500. Okay, hold on. Owen, you got $40? I got 20 right here. Come on, man. I don't want to eat my sandwich. I can go to Chipotle today, so come on. Trade? Are you in?
Coach, a Chipotle bowl costs like $12. It's not that serious.
I know, but I can get some rewards or something. I can buy 4 bowls. I gotta buy my math friends. Give me $40, man. Come on, I got 20. No? You're not in?
I'm all right, coach.
Anybody? Don't gamble. Just give me the money, right? I will flush it down the toilet for you. Save some time. Don't gamble. We are going to stop there for the day, okay? Because I want to give you a little bit of time. Take a look at those probability tests. Oh, yeah.